Welcome back to our ongoing exploration of the OEIS, the online encyclopedia of integer sequences.
It's a fascinating resource.
It is.
For anyone interested in the world of numbers.
Yeah, we're taking you on deep dives into some of the most intriguing integer sequences out there.
And today we're going to be tackling one that might seem a little abstract at first.
Yeah, 8700130.
But
it's a sequence that has some surprising connections to concepts.
You'll encounter in your number theory studies.
Yeah,
so.
I'm excited to jump in.
Yeah, me too.
The OEIS defines A000130 as 1/2 the number of permutations of length and with exactly one rising or falling succession.
It's a mouthful.
Yeah.
Right.
I had to take a second the first time I read that.
Let's break it down.
Yeah, please.
Piece by piece.
Okay.
So first,
all right.
Permutation.
Permutation.
What is a permutation?
Yeah.
It's simply an ordered arrangement of objects.
Okay.
So for example, if we take the letters A, B, and C, we can arrange them in a few different ways.
Yeah.
A, B, C, A, C, B, B, A, C.
Oh, I see. So
and so on.
It's all about the order of the elements.
Exactly.
Yes,
Each of those arrangements is a permutation.
Okay, cool. But what about this rising or falling succession part?
Right. So a rising succession
Yeah.
occurs when two adjacent numbers in the permutation increase.
Okay.
Like 1, 2, or 3, 5.
Go.
A falling succession is the opposite, where the adjacent numbers decrease, like 5, 3, or 2, 1.
Got it.
In A000130, we're interested in permutations that have exactly one instance of either a rising or a falling succession.
Okay, so for example, the permutation 132 would fit the criteria.
Perfect example.
Because it has one falling succession 3, 2.
Exactly. Okay. And to get the actual number for the sequence at a given position, n, we take the total number of permutations of length, n, that have exactly one rising or falling succession, and then we divide that number by 2.
All right, so let's look at the beginning of the sequence.
Okay.
0, 0, 1, 2, 5, 20, ...
Right.
To make this more concrete, can you walk us through how we arrive at that one?
Sure.
The third number in the sequence.
So for the third number in the sequence, n equals 3.
Right.
Meaning we're dealing with permutations of 3 elements.
Okay.
Let's say our elements are 1, 2, and 3.
Right, 1, 2, 3.
There are 6 possible permutations.
Okay.
123, 132, 213, 231, 312, and 321.
Okay.
Out of these,
yeah.
Only 132 and 233 have exactly one succession.
Okay.
132 has a falling succession, 3, 2.
Right.
And 213 has a rising succession, 2, 3.
Right.
All the other permutations have more than one succession.
Okay.
So we have 2 permutations that meet the criteria.
Okay.
We divide that by 2, and we get 1, the third number in the sequence.
Oh, wow. It's fascinating how quickly the number of permutations and potential successions increase.
Absolutely.
As n grows.
It gets complicated quickly.
It does.
And that's what makes this sequence so interesting.
Yeah.
It's a great example of how a simple rule can lead to complex patterns.
Yeah, it really is. And this sequence was compiled by N.J.A. Slime.
That's right.
The founder of the OEIS.
He seems to have had a knack for spotting these intriguing patterns and numbers.
He really did. It's incredible to think about the vastness of the OEIS. And the sheer number of sequences he helped document.
It's a monumental achievement.
Yeah. Now, there's another interesting aspect to A000130 that I think our number theory students will appreciate. There's a mathematical approximation for this sequence. A of n is approximately equal to e to the power of -2.
Right.
Multiplied by n factorial.
Yeah. The fact that we can approximate this sequence using factorial, something so fundamental to number theory, suggests there's a deeper connection there, a deeper structure to these permutations with one succession.
I like that.
And this approximation can also be really useful when dealing with large values of n.
Yeah, instead of having to calculate all the permutations and successions, for a large n, we can use this approximation
to
get a pretty accurate estimate.
It simplifies things.
It does. So this seemingly abstract sequence actually has practical applications.
Absolutely.
That's so cool.
And to further highlight its relevance, A000130 isn't just a mathematical curiosity.
Yeah.
It's actually referenced in research literature.
Really?
Mathematicians like David Kendall and Barton, who've made significant contributions to the field, have mentioned A000130 in their work on permutations and combinatorics.
So it's something that real mathematicians are using and thinking about.
Absolutely.
What's particularly interesting for our listeners is that A000130 has applications in the study of combinatorics.
Yes.
A key area of number theory that deals with counting and arranging objects.
Combinatorics plays a significant role in understanding arrangements and patterns.
Right.
And this sequence gives us a specific and interesting way to analyze those arrangements based on their rising and falling successions.
So interesting.
This makes it relevant to problems where the order of elements is crucial.
Yeah, it's a great point.
Right.
So cool.
It's not just theoretical, it has practical implications in various fields.
It's like we're getting a glimpse into how mathematicians use these sequences to solve problems.
Exactly. It is.
So cool.
It is, and this is where the connection to the factorial approximation becomes even more interesting.
Okay.
Remember, combinatorics is all about counting.
Right.
And factorials are fundamentally about counting, too.
Yeah.
Counting the number of ways to arrange a set of objects.
Right.
So the fact that we can approximate a 000130 using factorials hints at some deeper relationship between the structure of these permutations with one succession and the broader world of combinatorial problems.
So maybe a 000130 isn't just about these specific types of permutations.
Right.
Maybe it can tell us something about how order and arrangement work.
In a more general sense.
In a more general sense. That's pretty cool.
It is, and that's one of the things that makes the OEIS such a powerful tool. It allows you to explore these connections to see how different areas of math relate to each other in unexpected ways.
Absolutely. For our number theory students listening, you're going to be encountering permutations and combinatorics a lot in your studies.
It's foundational.
Yeah.
So having a solid understanding of these concepts is crucial.
For sure. And A000130 provides a really interesting lens through which to view those concepts.
It forces you to think about how the arrangement of numbers affects their properties and how those properties can be captured and quantified in a sequence.
Now, you mentioned earlier that A000130 is mentioned in research literature.
Right.
What can you tell us about how mathematicians are actually using this sequence in their work?
Well, for example, A000130 has connections to the study of pattern avoidance in permutations.
Interesting.
This is an area where mathematicians look for patterns that don't appear in permutations. And they analyze the properties of permutations that avoid certain patterns.
Got it.
It turns out that A000130 can be related to permutations that avoid certain patterns of length 3.
So by studying this seemingly simple sequence, we can actually gain insights into more complex patterns and structures within permutations.
Precisely. And those insights can then be applied to other areas of mathematics, computer science, even fields like genomics, where understanding arrangements and patterns is crucial.
This is really highlighting the practical applications of a sequence that initially seemed very abstract.
Right.
It's a great reminder that even in pure mathematics, there's often a connection to the real world waiting to be discovered.
Absolutely. And that's what makes exploring the OEIS so rewarding.
Yeah.
It's a constant reminder that even the most seemingly esoteric mathematical concepts can have surprising connections to the world around us.
That's a great point. Yeah, it's amazing to think that we started with a definition that seems so complex, and now we're seeing these connections to factorials, combinatorics, pattern avoidance, and even potential applications in other fields.
It really shows the power of mathematical exploration.
Yeah.
You start with a simple question, a simple rule, and it can lead you to these incredibly rich and interconnected concepts.
So to recap our deep dive today, we explored A00013, a sequence that counts half the number of permutations of length and with exactly one rising or falling succession.
Right.
We saw how it's connected to factorials, hinting at a deeper structure within these specific types of permutations.
Yes, and we discussed how A000130 relates to the field of combinatorics, a key area of study in number theory, and how it's being used by mathematicians to explore patterns and arrangements in a variety of contexts.
As you continue your journey in number theory, I encourage you to keep A000130 in mind.
It's a great example.
It is.
Of how a seemingly abstract sequence can unlock a deeper understanding of fundamental mathematical concepts.
And don't be afraid to explore the OEIs further.
There are countless other sequences waiting to be discovered.
So many.
Each of its own unique story to tell and connections to uncover.
That's right. So keep exploring, keep asking questions, and keep diving deep into the fascinating world of integer sequences.
Absolutely.
Until next time.